In this paper, we present an approach to interactive surface perception based on WSTac, a Whisker-inspired and self-illuminating vision-based tactile sensor. Stress sensing has been widely used in a variety of fields, from personal mobile phones to electronic touchscreens, automobiles, large machinery, and aircraft. On the other hand, a new round of technological revolution led by artificial intelligence, 5G communication, the Internet of Things, and biotechnology is accelerating its impact on human life. These emerging applications have resulted in diversified and specialized requirements for stress sensors. For example, in the fields of wearable devices and artificial intelligence, sensors should be more intelligent, energy saving, and flexible. For applications in biomechanics and engineering structural diagnosis, high spatial resolution and a fast response are important considerations. Visual-based tactile sensing, also known as VBTS, involves the use of optical systems to perceive physical contact or proximity. Despite the robustness of VBTS to influences such as temperature, magnetic fields, electric fields, and humidity, susceptibility to ambient light remains a concern as extraneous light sources can affect sensor stability. Therefore, in many recent VBTS researches, attempts to mitigate this limitation have involved blocking external light and introducing an internal LED lighting module to illuminate the sensor interior, thus enabling the camera to detect elastomer deformation. However, the inclusion of this additional lighting module necessitates supplementary electronic components and complex wiring, which can inadvertently lead to unnecessary energy consumption and heat generation. On the other hand, ML, short for mechanoluminescence, offers a unique transduction principle from mechanical energy to photon emission. A complete stress sensing route is constructed by combining the ML with photon detection. Thus, the photons emitted from ML materials act as intermediates in the ML-based stress sensing route. More importantly, the ability of photons to travel through space offers great potential for addressing the difficulties existing in advanced stress sensing, such as remoteness, spatial distribution, stretchability, and large area integration. So why not combine these two? We propose WSTac, a self-illuminating VBTS that integrates a mechanoluminescent whisker elastomer, a camera, and 3D printed parts. WSTac employs a whisker array and a camera to obtain dynamic tactile data without requiring LED modules, due to the elastomer's ML upon deformation. The ML whisker elastomer derives its inspiration from vibrissae, tactile hairs found in many mammals, recognized for their sensitivity to fluctuating contact variations. The ML whisker elastomer is a tri-layered composite with three distinct functions: external light isolation, emission of light upon deformation, and light guidance towards the sensor. Our whisker structure was validated via COMSOL multiphysics with a model involving an acrylic sphere of 0.5 mm radius sliding across a 1 by 5 mm Sorter-Clear 37 whisker with a fixed constraint at the base at 0.1 meters per second. The simulation result confirms the expected outcome of significant mechanical strain at the base of a single whisker, responsible for the mechanoluminescence photon emission, which mimics how sensory mechanoreceptors within the vibrissae follicle convert the movement of the vibrissae shaft into environmental contact data. WSTac's software component effectively identifies and extracts tactile signals from 25 taxons using camera imaging. This is achieved through pin detection in real-time tactile imagery with a resolution of 400 by 400, recognizing taxons equivalent to 50 unit squares. Given that taxons emit mainly green light, using the mean of the G channel for all pixels within the taxons divided by 255, we generate time series signals. In feature extraction, we aim to minimize the dimensions of multivariate time series, while differentiating 4 key parameters: direction, speed, and pattern, and depth of the surface. Our method is inspired by the electronic tactile sensor array's functioning, which uses a row plus column electrode structure to eliminate crosstalk and reduce the number of connection wires from I times j to I plus j. We adopt a similar approach for VVTS to decrease the algorithm complexity from theta I times j to theta I plus j. Furthermore, for enhancing data utilization based on sliding windows method, WSTac can autonomously detect valid tactile signals as seen in the above algorithm. Here we present to you 2 illustrations of the WSTac in action.